We started off the discussion of area, talking about Wally needing to buy soil for his raised beds. And we talked about area, finding the surface area of that. But to find the total soil needed, we need to know what the volume is, the total three-dimensional space of the raised bed that he needs to fill. So again, we've taken these three raised beds and combined them into this 48 square foot plot. And we have this area, but we also need to know the depth of soil required, because it's not just going to be a very thin layer of soil. We need a depth of soil there for the roots of the plants. So that we need to know the height or the depth of the soil, depending on what you want to think about it as. Suppose he needs 2 feet of depth in the soil for the raised beds. That means these things really look like this. They are 2 feet long, 8 feet wide, and 2 feet high, or 2 feet deep, whichever way you want to think about it. And there are, of course, 3 of them. So just like how we cut up the area into unit segments, into 1 foot by 1 foot unit segments, we can cut up the full 3-dimensional space into 1 foot by 1 foot by 1 foot unit cubes. So that's what this is doing here, and you can count them up. It's kind of hard to see if you're not familiar with visualizing this, but there are 4 unit cubes here, and then 4 here, 4 here, 4 here, 4, 4, 4, 4. In total, 32 1 foot by 1 foot by 1 foot unit cubes inside a single one of these plots. And so we need 3 of them. So we need 3 32 foot. 3 times 32 is just 96. Of course, you can just do 2 foot times 2 foot times 8 foot. That gives you 2 times 2 times 8 is 32. And then foot times foot times foot is 32 feet cubed. That's how we write that mathematically. So he needs 96 feet cubed of soil total. That's the space he needs to fill. And it says if bulk soil is priced at $30 per cubic yard, how much will it cost Wally for the soil that he needs? Well, he needs 96 feet cubed. We want cubic yards, however. So to do this, all we're going to do is do a unit conversion. We have feet cubed. This is over 1. And there is 1 yard is 3 feet. But I have to do this 3 times. And you can see that feet times feet times feet is the same thing as feet cubed. So we're going to get 96 divided by 3 times 3 times 3 is 27. Be yards cubed. And that gives us 3.5 repeating. So let's just do 3.56 approximately. And so that's how many cubic yards he needs. And if he has $30 per cubic yard, 3.56 cubic yards times $30 per cubic yard. And that gives us our dollar amount. $106.80 approximately, with that 3.56 approximation there. That's how much it'll cost him to fill these raised beds. Now, suppose a pool is 36 feet long and 18 feet wide by 6 feet deep. What is the volume of the pool? We have something like this. I'm trying to draw this somewhat accurately. It's going to be 36 feet long, 18 feet wide, and it's going to be like 6 feet deep, something like this. Trying to give you the perspective there. It's going to be 6 feet deep. And to find the volume, all we have to do for this one is just go, since these are all 90 degrees from each other, the height is 90 degrees, the length and the weight and the width. So the area or the volume of this pool is going to be 36 times 18 times 6. As long as they're orthogonal or at 90 degree angles, then all we have to do is multiply them all out. So we get a total volume of 3,888. This is going to be feet cubed. And we could do the same thing as I did up here, where we have the unit blocks. 1 foot by 1 foot by 1 foot. But the problem is here is that I just calculated it, and there'd be 3,888 of them. That's not easy to count in this example, so it's better to use the formula. That's the volume of the pool, 3,888 cubic feet. And it says how many gallons of water are needed if there are approximately 7.48 gallons per 1 cubic foot of volume. So we have 388 feet cubed over 1, and the conversion is 1 cubic foot has 7.48 gallons in it. 29,082, approximately that flat amount of gallons is required. So that's how many gallons of water would be needed to fill this pool. Now, just like area has different formulas for different shapes, volume also needs different formulas for different shapes. So you can see here, the cube is the most basic shape, just like the square is the basic shape in 2 dimensions. The cube's formula for volume is just length times length times length, because all the side lengths are the same no matter which side length you're talking about. It's always going to be the same length there for each one of these things. Now for a rectangular solid, like the pool we just solved, length times width times height, some of them could be the same, but if they're all different, that's fine. They're all at 90 degrees from each other. They're all orthogonal. That's how we say it in mathematics. So we just need to do length times width times height, and that gives us the volume of that rectangular solid. For a rectangular pyramid, this is rectangular because the bottom looks like a rectangle, or in this case, looks more like a square, but it can be a rectangular, a rectangle in shape. For this thing, we're going to do 1/3 length times width times height. So it's interesting that a pyramid having one side meet at a point just cuts the volume down by 1/3. Then a cylinder is the area of the circle, and then you're going to multiply that area by the height. That's how you fill this volume up, fill all these up with all these different circles here. You're going to add them all up. That's the same thing as repeat addition, same as multiplication. Pi r squared is the area of the bottom times the height is going to fill that volume up to give you this total volume of that shape. And then a cone is really where the sides of the cylinder just come together to a single point. And that's when we get a cone. And you can see that the cone is just, again, 1/3 the area of a cylinder. So it's very similar to how a rectangular pyramid is 1/3 the area of a rectangular solid. The cone is 1/3 of the cylinder. Finally, the sphere is the last interesting shape there. It is going to be 4/3 pi r cubed. Remember, the area of a circle is pi r squared. The sphere is going to be 4/3 pi r cubed. Okay, now the volume of this is a cube, of course. We're going to do 4 times 4 times 4, or 4 cubed. That's why it's called cubed, because it's going to be the same dimension times itself 3 times. So 4 times 4 is 16, times 4 is 64. And these are all in inches, so the unit of measurement we're going to get is inches cubed. Now a box is the same thing as a rectangular solid here. So this one here, length times width times height. Again, just like the pool example. So the volume of this is going to be the length of 2 feet times the width of 3 feet. That which name you give the sides doesn't really matter. Typically, the length is the longest side, but generally it depends on how it's oriented in the real life scenario. So the box typically has the height being the straight up sides going up to the opening of the box, and the base is going to be the bottom. And along the base of the bottom, the length is typically the longest side. It doesn't really matter though. All that matters is that we just need to multiply the 3 sides together, and that gives us the volume of this box. So 2 times 3 halves. This 2 and that 2 cancel. 3 times 3 equals 9. This is going to be feet cubed. That's the volume of that box. Okay, here we have a cylinder, and a cylinder is pi r squared, the area of the base circle, times the height of that circle, or of that cylinder. So we have pi r squared here. That's the base, and that's going to be times this height. So this is the height here, and this is the radius of the base. So pi r squared times the height of the cylinder. I'm getting 1,357, around to one place there. And the measurements are in centimeters, so we're going to have centimeters cubed. Okay, the volume of a sphere is 4/3 pi r cubed. R cubed, of course, r is 5 meters. That's the radius of the sphere. We're going to have 5 plugged in there for r. And I'm getting approximately 523.6 rounded to one place. The radius is in meters, so the volume is going to be in meters cubed. A certain scuba tank can be thought of as 24.8 inch long cylinder with a diameter 6.7 inches and a half sphere on top. So a scuba tank is going to have, it's going to be a cylinder, something like this. And it said this was, oh no, this distance was 24.8 inches. The diameter is going to be all the way across, is 6.7 inches. And then on top of this, right, is going to be a half sphere. So the full sphere would be all the way around, so we're going to take half of this volume. And this is also going to have that same diameter, right? This diameter is going to be 6.7 inches. And on top of that half sphere would be the valve that you plug your tubes into to get the actual oxygen out of it. And it says, what is the capacity of a cylinder in cubic feet? So we have inches here. We want cubic feet as our answer, so we have to keep that in mind. Now let's actually find the volume. We're going to find the volume of the cylinder. So cylinder is going to be, it's going to be the area of the circle on bottom. We have the diameter, so we need the radius, because we have pi r squared times h. The radius is half the diameter. That's going to be 3.35 squared times the height is 24.8. And the volume of the sphere, it's going to be the half sphere. So it's going to be, I'll say half sphere like this. It's going to be the volume of the full sphere, which is going to be 4/3 pi r cubed. R is again 3.35 cubed, and then we're going to divide that by 2 because it's half the sphere. For the cylinder, I'm getting 874.36. Of course, is in inches cubed. And then for the half sphere, I'm getting 78.74 inches cubed. So altogether equals 953.1 inches cubed. And again, it asks for the answer in cubic feet. So I need to do there is 12 inches to 1 foot. So I need to multiply that by itself 3 times. The inch cubed cancels, and then feet times feet times feet gives us feet cubed. I'm getting 0.55 rounded to 2 places, feet cubed for that capacity. Now, if you were to look up the actual volumes of scuba tanks, you can see that they have way bigger volumes than this feet cubed, probably like 80 or 100 feet cubed. That's because they're talking about pressurized oxygen. This is just the physical volume of the space. So you actually have to do a conversion between how pressurized the air is and everything to actually find the amount of oxygen you can actually need or you can actually store into there, but it's going to be under pressure. So that's the difference here. This is just the physical volume, or they call it a water volume, this is how much water would actually fit in the tank if you were to fill it full of water. Okay, now according to Wikipedia, the Great Pyramid of Giza is 138.5 meters tall with a square base. So it's got a square base. And it's got a square base of side length 230.3 meters. What is the volume of the pyramid? So we know that we have a square pyramid since it's going to be a square base like this. And then all these points come up to meet at a point there at the top. Now, we know that it's going to be 230.3. Let me just show you a side, kind of a side drawing of this, right? This would be just like a pyramid here. The square base of 230.3. All the way around, that's what the square base means. And then it says the height of this pyramid, so the height of it is 138.5 meters tall. And the volume of a pyramid is going to be 1/3 the volume of a rectangle. The volume of a rectangle is length times width times height. Well, length times width times height, they're all the same measurements because, well, the length and the width are the same measurements because it's a square pyramid. It's 230.3 times 230.3. So we get 230.3, 230.3, or 230.3 squared, times by the height measurement. The height was 138.5. Okay, so let's actually calculate that. 2,448,591.82. This is going to be meters cubed, right? Because everything's in meters. And this, of course, is the pyramid that's above the surface. There could be stuff underneath the surface. We're not calculating that because we don't know the dimensions of that. Okay, Rachel needs to make 300 cupcakes for a wedding reception, and she's going to pipe buttercream frosting on the top. So she's got to figure out how much to make. Frosting can be approximated as a cone, right? We have a cupcakes like this, and then the cone of frosting goes on top. We're just going to approximate with a sharp cone. Of course, it's going to be more like variance in there because they're going to, she's going to have air inside the pipe and then, going to make the swirls and everything like that. But it's a good approximation. It kind of fits the look of it. Now, she's going to approximate the cone measurements, going to be 2¼ inch diameter. So this length here of the cone is 2¼ inch. And then the height is going to be 2 inches. Okay, how many gallons of frosting are needed at a minimum if there is 1.8 inch cubed, since we're talking about inches here, inch cubed is about 1 fluid ounce, and then 128 fluid ounces is 1 gallon. So we're going to find a volume, a liquid capacity of frosting. Okay, so we have a cone here, and the volume of a cone is going to be 1/3 the volume of a cylinder with the same dimensions. So the volume of a cylinder is going to be half, right? We have to use the radius. It's going to be pi r squared times the height. Well, r is 2¼ That's the same thing as 9/4. So I need to divide that by 2. Same thing as multiplying by 1/2. It's going to be 9/8 times by the height of the cone, which is going to be 2 inches. So that's the volume of this frosting. Doing that, I get, so that's the volume for 1 cupcake. We have 3 of them we have to find. So 2.651 inch cubed times, not 300 of them. 795.3 inches cubed. So we're going to figure out how many gallons of frosting is necessary. So first off, we're going to do the unit conversion between inches cubed and fluid ounces. There's 1.8 inches cubed in 1 fluid ounce. I'm going to multiply that by 128 fluid ounces in 1 gallon. And now you can see the fluid ounces cancel and the inches cubed cancel. And you have just gallons as our unit measurement. So let's go ahead and solve that. 3.452 gallons of frosting is required. Of course, gallons might not be the best unit measurement there. It depends on what they're used to using. It could be a weight that they prefer using instead of the gallons. That, of course, depends upon the buttercream frosting, or maybe it's a cream cheese frosting, whatever it is. That varies depending upon the recipe. But this is just a volumetric measurement. 3.52 gallons, maybe 3.5 gallons, maybe 4 gallons is what you need if you make mistakes, that kind of stuff. I'm not sure. That really depends upon the expertise and the style that the person is doing. All right, for this last problem, we have the volume of Lake Superior can be approximated with a trapezoidal prism, which is really just taking this trapezoid that approximates the surface area and then creating a depth to it. So that's what a prism is. It's just a shape, a two-dimensional shape, and that's extended in 3 dimensions with a certain height measurement. And that's what's given here, well, in this case, depth measurement of 483 feet. So we still have a trapezoid. On the top half, we're going to find the area of the trapezoid and then multiply it by the depth. And that gives us the volume of this trapezoidal prism that we're estimating it with. So the area of a trapezoid is going to be base 1 plus base 2 over 2 times the height. The height's a straight line distance between 2 bases, and that's given to us here, of course. The height is 145. We can say base 1 is 102, and base 2 is 354. So the area of the trapezoid is going to be 102 plus 354 over 2 times the height of these trapezoids. That gives us 33,060. And it's going to, of course, going to be in miles squared. And this is the surface area of the lake. Now we need to find the volume, the measurement of the volume of the water capacity in this. And here we have, we're going to multiply this surface area by the depth, which is 483 feet. The issue here, of course, is that we have an area measurement of miles squared and a depth of feet. So we need to change the feet into miles so we have a miles cubed metric. That's what we want to use for the volume. That's going to be the miles of the trapezoid, and then we're going to multiply that by the depth here in miles, which is the same thing as 483 feet divided by 5280. That's how many feet are in a mile. 3,024. We're just going to round to the whole place here. This is going to be miles cubed. So that's our estimation. And it says, what is the percent change from this amount from the volume of 29,000 miles cubed established by the EPA? That's what they say the capacity here of Lake Superior is. So for that, we're going to do final minus initial over initial. That's one way of calculating it. 3024 minus 29,000 over 29,000. Or sorry, 2,900. What I should be saying there. 0.0428, which means that our estimation is 4.28% above. It's a percentage increase, so it's 4.28% above the real amount. So it's actually a fairly good estimation. It's not that far off. It's not like 50% off, right? It's not 100% off. Yeah, it's fairly close to it. So and this was using just simple geometry techniques, not using any kind of shoreline calculations where you worry about where the shorelines are here and all that kind of stuff. We're just basic estimation gets us pretty close to the actual one.